Inverse relations and functions. Two functions f of x and g of x are inverse functions if and only if f of g of x will give you back x and g of f of x will give you also back x. Let's get started. Inverse relations and functions. To find the inverse function, we follow the following steps. Step number 1, we replace f of x with y for the convenience. Step number 2, we exchange x and y. We switch x and y. And the reason we exchange or switch x and y is the inverse mode. Your input becomes your output, and your output becomes your input. Your domain becomes your range, and your range becomes your domain. And that is behind the reason why we exchange x and y. Now we solve for y, that's the new y in step number 3, and finally we call it f inverse. Now of course we have to restrict the domain of f of x and f inverse of x so that f of x and f inverse are functions. And we could graph it to show you that f of x and f inverse of x are reflections of each other about the line y equals x. And I do have 4 examples. Example number 1. Find the inverse of f of x equals negative half x plus 1. Here's step number 1. We replace f of x with y. This becomes y equal negative half x plus 1. Step number 2, we exchange x and y, switch x and y. This becomes x, negative half, instead of times x we say y, plus 1. And step number 3, we solve for y. To solve for y, we subtract 1 from both sides. And of course, when we subtract 1 on the left, we can't combine them, so we end up with x minus 1. So we say x minus 1 on the left equals negative half times y. To solve for y, I need to multiply the right-hand side by the reciprocal. So let's write x minus 1 right here. We multiply by the reciprocal. That's negative 2 over 1. To leave y alone, of course we have to do it both sides. The right-hand side simplifies to 1y. The left-hand side is negative 2 times x and times negative 1 using the distributive property. We end up with negative 2x, and negative 2 times negative 1 is plus 2. That is step number 3. Step number 4, replace y with f inverse of x. So I have negative 2x plus 2 equals f inverse of x, or differently we say f inverse of x equals negative 2x plus 2. Just to verify that this is the inverse, we could do the following. Let's say we plug in the function f of x right here, which is written also right here, plug in 0. What do we get? Negative half times 0 is 0, plus 1 will just give you 1. Now in the inverse down below, if we plug in 1, we should get back 0. To plug in 1 right here, I get negative 2 times 1, which is negative 2. Negative 2 plus 2 is 0. Just to verify that Yes, we are in the inverse mode. That is the inverse. Of course, that's not enough. So let's support that graphically. The first function f of x is negative half x plus 1, which means we have a y-intercept of 1 and the slope, which is negative 1 over 2. We're going to go down 1 and run 2, and the graph should look something like this. That's f of x. We had f inverse of x equals negative 2x plus 2, which is negative 2 over 1 x plus 2. The y-intercept is 2, and the slope is negative 2 over 1. So we're going to go down 2 over 1 and connect them. So if you connect them, clearly we have something here that shows we are having a reflection about y equals x. Let's clean it up and show you the graph in detail. Here's the first function, or the original function, graphed, starting at 1 y-intercept, going down 1 over 2. And here's the inverse in blue color. You start at 2 and you go down 2 over 1. And this is with y equals x, the line of reflection between a function and its inverse. And that should do it for number 1. We did not have to restrict the domain because both functions, the red and the blue, are functions with the vertical line test. Example number 2. Find the inverse of f of x equals x to the second plus 2x plus 4. This one is quadratic, which is a little bit different. So let's follow the steps and see what we could do. We have f of x equals x to the second plus 2x plus 4. And step number 1, we will call it y for the convenience. So it's y equal x to the second plus 2x plus 4. We need to exchange x and y for step number 2. So this becomes x, and this is y to the second plus 2y plus 4. To solve for y, we need to complete the square, and I'll show you what we mean by this and why we need it. So y to the second plus 2y. Let's push the 4 to the right side. Now, I do have b equals 2. To complete the square, we go to the side and we take b, which is equal to 2. We take half of that, which is 2 over 2, and that's a 1. We square half b. That's a square of 1, which is still 1. So we have x equal y to the second plus 2y, and we have plus 4 to the side, and we are adding 1. Now, of course, if you add 1 to the right side, you have to add 1 to the left to keep it balanced. So we are trying to solve for y, which is step number 3. We are trying to solve for y. Left hand side is x plus 1. Right hand side is y. We're doing the following, which is called in math perfect square trinomial. So I do have a perfect square right here, trinomial. The trinomial is given. I need to write the perfect square. As you could see, we could think about y square comes down to y, and a square comes down to a. So y square comes down to y, and 1, which is a square, comes down to 1. We leave the 4 on the side. So I have y and 1. Bring the 4 down, and that's what we have. Now, subtract 4 from both sides, because we're solving for y. Subtract 4. On the left side, it's x minus 3. On the right side, it's y plus 1 to the second, because the 4 cancels. These 4 cancels. Let's rewrite it the other way around, because the focus is on y. Y plus 1 to the second equals x minus 3. To solve for y, I'm gonna apply the square root to both sides. And to do that, we have to be careful and add the plus minus. Now, on the left side, it's just y plus 1. On the right side, it's a plus minus square root. Let's go to the side and finish it. Subtracting 1 from both sides, I get the following. I have y by itself on the left equals minus 1 plus minus square root of x minus 3. Now this is not the inverse, because I do have a plus minus in my way, and that's not supposed to stay there. This plus minus makes this a relation, not a function, because a function is defined to have for every input exactly one output. To have it in inverse, and pay attention to this comment right here, now we call it the following. F inverse of x is, so we are in step number 4, equals -1 plus, only the plus sign, square root of x minus 3. Let me support that graphically and show you exactly what's going on with the quadratic equation given to me and the inverse that has a square root. So, our original function is f of x equals x to the second plus 2x plus 4. And if you complete the square, I have this, and I push the 4 to the side. This is my b, which is 2. I take b to the side. I take that and divide by 2. 2 over 2 is 1. b over 2 to the second will be 1 to the second, which is also 1. So I go back to the problem, and I say we have x to the second plus 2x plus 4. We add 1 and we subtract 1 to keep it balanced. Now what's happening is the following. This right here is a perfect square trinomial. That could be rewritten as a perfect square. Y square comes down to y, and a square comes down to a, x square comes down to x, and 1 square or 1 comes down to 1. On the right side, I do have 4 minus 1, and that's a 3 right here. So we're going to write plus 3. So that's a vertex form, easier to graph. That means it's a quadratic equation with a equals 1, shifted to the left 1, and shifted up 3 units. That means the vertex is at -1 and 3. that is the vertex with a normal opening. So it's going to go right here and right here. That is f of x. Now we came up with f inverse of x, which was minus 1 plus, without the plus minus, square root of x minus 3. That is a square root shifted to the right 3 units and shifted down 1 unit. So we are having a square root that starts right here and goes through this point. Well, to restrict the domain of f of x, this has to be eliminated. This right here. That should be out. To make it clear, I have the following. So originally we have the function with domain or real numbers, but once you reflect it about y equals x right here, it gives you this graph, but that's not a function because of the vertical line test. It doesn't pass the vertical line test. So we only want to keep this, which is the plus. We do eliminate the minus sign, and we go back to the function and take this off, restricting the domain. The domain should become only from -1 up. So the function f should have a domain only from -1 to infinity to give me the inverse. And this is, what do I mean? The original function has the domain restricted from -1 to infinity. The inverse will be the -1 plus the square root of x minus 3. And that's clearly a reflection about y equals x. For question number 3 and number 4, we have two functions, and we need to verify if they are inverse of each other. Number 3. Determine whether f of x and g of x are inverse functions. F of x equals square root of x plus 3. Take 2. Number 3. Determine whether f of x and g of x are inverse functions. F of x equals square root of x plus 13, and g of x equals the square of x minus 13. It looks like they're inverse of each other because one is adding 13 and one is subtracting 13. One is taking the square root and one is squaring. But that's not how we verify. We have to follow the rule. So the question is, we want to find if f of g of x equals x, if it gives me back x. So let's start on the left hand side. We have f of g of x. And let's write g of x in a different color. And we want to see if that gives me back x. So we have f of, and g of x is written to me as x minus 13 to the second. So we're going to write that as x minus 13 to the second. Now, the function f says to me, anything I give you, you add 13 to it, and once you're done adding 13, you put that under the square root. So we need to follow the rule and add 13, applying the function f, and once we're done, we're gonna take the square root. That's applying the function f. So what's given to me is x minus 13 to the second. And to do that, we could pay attention to the following. The perfect square trinomial, x minus a to the second, will give me 3 terms. So that is this right here. That will be replaced with 3 terms right here. So here we go. Equals square root with plus 13 on the side. That x minus 13 to the second will give me 3 terms. X to the second minus twice ab, or twice a times x, and I have x and minus 13, so 13 is replacing a. Minus twice that much multiplied together, that's minus 26x plus a to the second, which is 13 squared, and that's 169. Simplifying, I have x to the second minus 26x. 169 plus 13 is 182. Now clearly this is not equal to x. There is no way I could simplify this and make it equal to x as we're looking for, which means this implies that f of x and g of x are not inverses. That should do it for number 3. The last problem, number 4. Determine whether f of x and g of x are inverse functions. F of x is 2x plus 3 and g of x equals half of x minus 3. Applying the rule that we are looking at on the right side, I have it separate in 2 parts. So let's do the first one. So we're thinking if this is going to give me back x. We start on the left, f of g of x. Let's use g of x in a different color. And equal f of, instead of g of x, we write what we know about g of x from the top right here. That's half times x minus 3. Now, to apply the function f right here, we need to think this way, which means anything is given to us, we multiply it by 2, and once we finish, we add 3. So the function f says anything you're given, you multiply it by 2, and once you finish, you add 3. But we are given half times x minus 3. Now if I multiply 2 times half, that's going to simplify to 1. So I have the following. I have 2 multiplied by half times x minus 3, and we have plus 3. These 2 will simplify to 1. That 2 and a half, and that will give me just 1 multiplied by x minus 3 plus 3, which is just x minus 3 plus 3, and the minus 3 and the plus 3 cancels, and that will give me x as expected. To do it the other way around, that's g of f of x, and we want to see if it gives me back x. That's the question. Let's change the color inside and call it f of x in light green. That is my g of x, my f of x. So I have g of, that's equal, instead of f of x, we write 2x plus 3. Now, applying the function g says anything you are given, you subtract 3 from it, and once you finish subtracting 3, you multiply it by half. So applying the function g, we're going to subtract 3 from what's given to us and then multiply by half. But we are given 2x plus 3. Inside, it just 2x plus 3, and we have a minus 3. There is no need for the parentheses. I just had them to show you the substitution. We could cancel the 3 and the minus 3, and we have half times 2x, which is just x as expected, or what we're looking for. Clearly, that says that f of x and g of x are inverses. And that should do it.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.